Hi, I'm Neil deGrasse, and today I'm going to tell you 100 facts about space disasters that could happen. Subscribe, and let's get started. Number one, an asteroid only a few hundred meters wide could destroy civilization. A rock just 300 meters wide is small in space, but huge for Earth. If it hit land, the blast and fire could level a whole region. If it hit the ocean, big tsunami waves could slam coastlines. That's why scientists flag anything bigger than 140 meters as a serious hazard. Models show 300 to 500 meters objects can cause continental scale damage. Ocean impacts can launch powerful waves and floods near the coasts. Size isn't everything. Speed plus mass is huge energy. Number two, asteroids classified as potentially hazardous. Asteroids this small can still hit with the power of thousands of nukes, wiping out a city and kicking dust into the sky for months. NASA watches these closely. Objects more than 140 meters that pass near Earth are classed as potentially hazardous because of the damage they could cause. Impacts this big are rare but not impossible, so finding them early is a big deal. Number three, a nearby supernova nearly 30 light years. If a star exploded very close, tens of light years, its X-rays and cosmic rays could chew up Earth's ozone, letting extra UV reach the ground. Bad news for life. Studies suggest especially bright X-ray heavy blasts could be dangerous out past 100 to 160 light years, and mass extinction risk rises inside 30 to 50 light years. The good news, no known star that close is about to blow. Number four, tiny space dust that can hurt big satellites. Space is full of micrometeoroids, grains smaller than sand, zipping faster than bullets. A single speck can pit mirrors, punch solar panels, or nudge a satellite off aim. NASA designed spacecraft to withstand these hits and even adjusted operations after James Webb Space Telescope took a notable micrometeoroid strike in 2022. These showers don't rain fire, but many tiny dings over years can add up. So engineers model, shield, and plan. Number five, a sudden burst of space radiation. Sometimes the sun or a star explosion far away sends a spray of superfast particles toward Earth. When that spray hits our air, it makes extra electrical sparkiness up high, which can mess with radio and GPIEs and even bug satellites for a while. Scientists have names for these blips. A quick spike measured at the ground is a ground level enhancement. And a sudden dip after a solar blast is a four-bush decrease. Space weather teams watch for these particle bursts and send alerts so pilots, power grids, and satellite folks can prepare. Number six, how solar particle blasts nibble at our ozone. Sometimes the sun spits out a storm of fast protons that hits Earth's air near the poles. Those particles make special chemicals with nitrogen and hydrogen that can break down ozone, our sky's UV shield, for a short time. Scientists saw this during big solar storms like the 2003 Halloween events, where polar ozone dipped for days to weeks, then recovered. It's not like the long-term human-made ozone problem. This is temporary and mostly polar. But it can still matter for satellites, radio, and flights over high latitudes. Number seven, a solar mini-nova, not how our sun works. A nova happens when a white dwarf star steals gas from a neighbor and that stolen gas explodes. Our sun isn't a white dwarf, so it can't be a nova. What can the sun do? It makes flares, and very rarely sun-like stars make superflares. Scientists have seen superflares on sun twin stars and estimate about once per century per star on average. If a superflare hit Earth, it would mean extreme space weather, trouble for satellites, radio, GPIEs, and power grids, but still not a nova. No mini-nova sun, just flares, and we prepare for those. Number eight, big impacts from 1 to 5 kilometers can chill the whole planet. When a 1 to 5 kilometer space rock hits land, it blasts dust and smoke high into the sky, blocking sunlight. That makes Earth cooler and darker for years. An impact winter. Computer models for a 500 meters asteroid half a kilometer already show global cooling by a few Celsius degrees, less rain, and stressed plants, so 1 to 2 kilometers would be even worse. Cooler, dimmer weather means poor harvests and food shortages around the world. The exact effects depend on where it hits, land, ocean, icy area, and how much soot and dust reach the stratosphere, but the global chill is the big worry. Number nine, the indirect effects of asteroid impacts. Even if a space rock doesn't hit a city, a big splash in the ocean or a remote land strike can throw dust, soot, and vapor high into the air. That gunk can block sunlight, cool the planet for years, and stress food chains. An impact winter. Studies of past giant impacts like Chicxulub and new simulations show fine dust and soot can drive the long, cold dimming more than anything else. So the blast is short, but the after effects can be the real trouble. Number 10, an Earth-directed coronal mass ejection. A CIMI, or coronal mass ejection, is a giant blob of gas and magnetic fields the sun throws into space. These blobs can race toward Earth and arrive in about 1 to 3 days. When one hits our magnetic bubble, it can stir up a geomagnetic storm. That storm can mess with power grids, satellites, IPEs, and radio. Space weather centers watch the sun, post alerts, and rate storm strength on handy scales: GI for geomagnetic, ES for radiation, R for radio. A CIMI is the sun's magnetic sneeze, beautiful in the sky, but tough on our tech, so experts track and warn us in time. Number 11, gamma ray bursts aimed at Earth. A gamma ray burst, or GRB, is a powerful explosion from a collapsing star. If one were pointed at us, it could strip ozone in the upper air and flood the surface with extra IUV, stressing life. It's very rare, but it's a top example of extreme space physics that nature can deliver. Number 12, the giant meteor shower. Big rock showers could happen if a comet breaks into many pieces, sending multiple large fragments our way, just like Comet Shoemaker-Levy 9, which hit Jupiter in a dramatic string of impacts. That's why NASA tracks potentially hazardous objects bigger than 140 meters so we can spot threats early. Number 13, could a giant impact set off lots of volcanoes at once? A huge asteroid releases planet-wide energy, cracking rocks and shaking Earth. Think global megaquakes. Some studies propose the dinosaur-era impact helped ramp up Deccan Traps volcanism. More lava for thousands of years, showing how a space hit could stress Earth's mantle and trigger extra eruptions. Number 14, when a nearby star explodes, its shock can touch us. A supernova sends out a wave of energy and fast particles that can make Earth's upper air extra electric and nibble at our ozone for a while, which can bother satellites, radios, and even change how much IUV reaches the ground. The closer the blast, the bigger the effect. Models show serious ozone loss if an explosion happens within a few dozen light years. Number 15, how sunlight can make a planet lose all its water. Strong sunlight in the upper air can break water into pieces, 1 oxygen and 2 hydrogen atoms. The tiny, light hydrogen can then leak away to space. And if this keeps happening for a very long time, the planet can dry out. That's one way Mars lost a lot of its old water. Spacecraft saw hydrogen escaping faster when Mars is closer to the sun, and during dust storms that loft water higher where light can split it. Over billions of years, that slow leak adds up. Sunlight snips water, hydrogen drifts off, and the world thirsts. Number 16, long dimming by dust. After a huge impact on Earth, dust and soot can rise high and block sunlight for months to years. Cooling the planet and hurting photosynthesis, we found evidence of rapid cooling after the Chicxulub impact that ended the dinosaurs. The exact effects depend on how much dust/soot gets lofted and how long it stays aloft. Number 17, if a giant rock hits the moon has no air to slow space rocks, so a big hit would make a huge blast and a new crater, tossing lots of moon bits into space. Some fast pieces can escape the moon's gravity and later fall toward Earth. That's how we get lunar meteorites to study. Recent studies even suggest a rare impact could spark a short moon rock meteor shower at Earth if enough debris gets launched. Number 18, when the moon gets whacked, tiny moon rocks can fall on Earth. If a space rock slams into the moon, the smash can throw bits of the moon so fast they escape its weak gravity and drift through space. Some of those bits later fall on Earth. We call them lunar meteorites, and scientists study them to learn moon secrets without going back there. Number 19, what if something big hits Jupiter? Jupiter is so huge that when a big rock or comet slams in, it can make a flash and a dark bruise you can see with telescopes from Earth. This really happened in 1994 with the comet Shoemaker-Levy 9. The crash blasts fireballs and shockwaves through Jupiter's clouds and stirs its weather. Scientists even track the plume and waves racing through its atmosphere. Nearby moons can feel the jolt through changing dust and charged gas around Jupiter, and leftover pieces can be captured by Jupiter or flung on new paths around the sun. Number 20. If Earth got kicked out into space. If a huge gravity shove ever pushed Earth away from the sun, our world would turn into a rogue planet. No sunlight, just the faint warmth from inside the Earth. The surface would freeze fast, oceans would ice over from the top, and most air would condense as frost because the sun's heat, which normally supplies almost all our energy, would be gone. Deep below the ice, a little geothermal heat might keep some water liquid for a while, but the surface would be dark and bitterly cold. Number 21, if a space rock hit near a Mars base. Mars has very thin air, so even small meteors can stay fast and punchy. A nearby hit could damage habitats, kick up toxic dust with things like perchlorates, and shake the ground. InSight actually heard real meteoroid impacts on Mars. That's why future bases need shields, sensors, and safe rooms to keep people and gear okay. Number 22, we can push space rocks. DART proved it. NASA's DART spacecraft hit a tiny moon called Dimorphos on purpose. After the hit, Dimorphos' orbit got shorter by about 33 minutes. That shows a kinetic push can change an asteroid's path, a real tool for planetary defense. It's like giving a rolling ball a tap so it misses the vase. Result? Earth can defend itself if we find a threat early. Number 23, and the target even squished. Follow-up studies found the crash reshaped Dimorphos' little world. It went from more ball-like to a bit stretched. And its orbit changed shape too. That tells engineers how rubble pile asteroids behave when you bump them. Super useful for future deflection missions. Number 24, a mega collision can shake Earth's spin. Long ago, a Mars-sized rock likely smashed into baby Earth and the flying debris made our moon. That's the big hit idea most scientists use today. That smack also sped up Earth's spin, so a day may have been only a few hours at first. As time passed, the moon's tug slowed Earth down for 24 hours and helped keep our planet's tilt fairly steady. Remember, that is the reason why we have seasons. A blow that big can also stir the inside of a planet. The hot, swirling metal that helps make our magnetic field. So the field could wobble for a while after such an event. Number 25, satellite chain crash, the Kessler syndrome. In orbit, things move crazy fast. If one satellite shatters, its pieces can hit others, making more pieces, a domino effect called the Kessler syndrome. We've seen how bad one smash can be. The 2009 Iridium Cosmos collision made thousands of trackable fragments that lingered for years. More debris means more collision risk for GIPS, weather, and internet satellites, so space agencies now design for safety and cleanup after missions. For example, IESAI tightened rules so new low-orbit satellites deorbit within 5 years instead of 25. To cut the chance of smash-ups, think of it like a busy highway. We need good rules and cleanup so one crash doesn't jam the whole sky. Number 26, what if a mega constellation fell back to Earth? Most falling satellites burn up high in the air, so the ground risk is tiny but not zero. Safety rules limit the chance of hurting someone to 1 in 1,000,000 per re-entry. And space agencies plan controlled deorbits when they can. As we launch more spacecraft, experts track casualty risk and push stricter debris mitigation rules like deorbiting within 5 years to keep space safe. If many satellites re-enter together, small bits could reach the surface or clutter the orbit, so continuous monitoring and cleanup policies matter to prevent orbital traffic jams. Number 27, how are satellites removed from space? Old satellites are retired in two main ways. If they're in low Earth orbit, operators drop them down so they burn up in the air, sometimes guiding big pieces to the remote South Pacific spacecraft cemetery near Point Nemo. If they're in geostationary orbit, they go up a few hundred kilometers to a safe graveyard orbit and are shut down so they won't bother working satellites. When a craft can't steer anymore, teams may let atmospheric drag bring it down over time, and new space cleanup missions aim to grab and remove dead hardware. Number 28, if weather satellites all failed at once. Weather satellites are our eyes in the sky. They watch storms, feed computers with measurements, and help warn people early. If many of them stopped together, hurricane and storm warnings would get worse, planes and farmers would get poorer forecasts, and rescuers would lose real-time maps. That's why agencies keep backups and fight to keep key data flowing, even when old satellites are retiring. Number 29, a nuclear leak from a satellite. Some old satellites use small nuclear reactors for power, so space agencies have strict safety rules for using nuclear power in space. A famous case, Cosmos 954 broke up and fell over Canada in 1978, spreading radioactive debris on the ground. Teams had to clean it up. If a reactor satellite leaked in orbit or re-entered, it could threaten nearby satellites, astronauts, and if pieces survive people on Earth. That's why modern missions plan shielding, constant monitoring, and safe deorbit steps. Number 30, if the space station lost control. The ISS must point the right way to stay safe. Tiny spinning wheels and, when needed, thrusters keep it steady and in the right orbit. If it drifted or spun, docking ships would be hard and many experiments wouldn't work right. so controllers would quickly use thrusters to fix it. We've even seen a scare. In 2021, a new module's thrusters fired by mistake and the ISS tilted, but teams regained control and the station was fine. Number 31, space debris versus airplanes. How risky is falling rocket junk? Think of the sky like a busy highway. Old rocket pieces sometimes fall back down. Scientists mapped where planes fly most and found that in very busy airspaces, like the IUS Northeast or parts of Europe and Asia, there's about a 1 in 4 chance each year that a falling rocket stage will pass through that big region of sky. That doesn't mean it hits a plane. Actual hit risk to any one aircraft is still very small. But it's enough that pilots may need reroutes or brief closures. Number 32, old space stuff comes home. Some broken spacecraft don't burn up right away. They circle Earth for decades. A Soviet Venus lander piece called Cosmos 482 finally re-entered in May 2025 after 53 years and splashed into the Indian Ocean. Agencies watched it closely. It wasn't very dangerous, but it shows why we track old hardware and plan safe re-entries. Number 33. The sun gets giant and may swallow Earth. In about 5 or 6 billion years, the sun will run out of easy fuel and puff up into a red giant. It will likely swallow Mercury and Venus, and maybe Earth, or at least scorch it so badly that oceans and air are lost. After that, the sun will shed its outer layers and become a small, faint white dwarf. This sounds scary, but it's far, far in the future, long after humans, and it's just how stars like our sun age and change. Number 34, solar flares during busy sun times. When the sun is in its active phase, called solar maximum, it pops more flares and launches more CIM, big blobs of magnetized gas. If several CIM are piled up, a cannibal CIMI, the resulting storm at Earth can be stronger, boosting auroras and bugging power grids. GPS and radio. Number 35, neutron star smash-ups or kilonovae. 2 tiny, super heavy stars can crash together and make gravitational waves, ripples in space we can hear, and a bright blast called a kilonova. These mergers also make a quick gamma ray burst and even forge heavy elements like gold, space's sparkle factory. If one happened very close to us, the high energy rays could thin Earth's ozone for a while. Letting in extra IUV, tough on life, dangerous nearby ones are rare, and the famous 2017 event was 140 million light years away. Number 36, extreme solar burnout, far, far in the future. The sun will slowly get brighter and hotter as it ages. Even before it becomes a red giant, that extra brightness will nudge Earth's air into a moist greenhouse state, letting water escape to space. Over about 1 billion years or more, this could dry out the oceans, making Earth too hot for life long before the red giant phase. Later, in roughly 5 or 6 billion years, the sun will puff up into a red giant. Bad news for the inner planets. The sun brightens, oceans fade, and much later the sun swells up. Number 37, could an asteroid trigger supervolcano eruptions? A giant asteroid smack like the one that hit 66 million years ago can shake the whole planet? Some scientists think that jolts may have sped up huge lava eruptions in India, the Deccan Traps, a 1-2 punch with the impact. Other studies test how super eruptions change climate and how big the cooling really is. So, an impact might help trigger extravolcanism, but it's still an area of research. Either way, both big impacts and super eruptions can be tough on life and weather. Number 38, extreme solar eruptions even in quiet times. The sun has calm years and busy years, but big storms can still happen in quiet stretches. Space weather is tricky. A famous example is the 1903 superstorm, which struck near a solar minimum and still ranked among the strongest on record. NASA explains that CIMs can race out and shake Earth's tech even when we're not at peak activity. Scientists now track surprises like space hurricanes during quiet days, too, another reminder to prepare, not panic. Number 39, Oort cloud instability. The distant Oort cloud is a huge shell of icy bits. Passing stars and the Milky Way's gentle tug can stir it, sometimes launching big comets toward the inner solar system. That's normal over long times, and scientists model these nudges to understand comet showers and impact risks. Number 40, a wandering star passes nearby. Sometimes stars fly past our solar system. One called Schultz's star likely skimmed the Oort cloud 70000 years ago, and Gliese 710 is predicted to pass within the Oort cloud in 1.3 million years. Such flybys can jiggle comets, sending some inward. Most miss us, but a few could become new long-period visitors. Number 41, what happens if Earth's magnetic shield weakens? Earth's magnetic field is like an invisible force field that guides compasses and helps block some solar and cosmic radiation. When it weakens, during strong space weather events, satellites, power grids, radio, and GPIAs can misbehave, and high-flying crews or astronauts can get extra radiation. Birds and other animals that navigate by magnetism can also be confused. The shield can wobble, but we watch it closely. Number 42, magnetic pole flip, the geomagnetic reversal. Sometimes over thousands of years, Earth's magnetic north and south slowly swap places during parts of that flip. The field can be weaker, letting more radiation reach near Earth space and tough on satellites and GPIAs, but it doesn't make the atmosphere vanish. Past short flips like the Lachamp event that happened 42000 years ago show big drops in field strength for a while. Then recovery. Number 43, extreme droughts from a dip in sunlight. The sun's light wiggles a tiny bit over an 11-year cycle, about 0.1%, and during extra quiet times, Earth can cool a little. That small cooling can nudge winds and monsoons, sometimes lining up with drier seasons in places that depend on monsoon rain. Historical studies even find more drought episodes during the Dalton minimum. It's not the only cause, big volcanoes matter too, but solar dips can shift rain belts, making some regions thirsty for a while. Number 44, what is the Dalton minimum? The Dalton minimum was a time about 1790 to 1830 when the sun had fewer sunspots than usual. So its light wiggled a tiny bit lower. That small dip can gently cool parts of Earth and nudge weather patterns, but it wasn't the only cause of chilly years. Big volcanoes like Tambora in 1815 blasted sun-blocking ash that made things much colder. Scientists tracked this period with sunspot counts and solar energy records, and they agree it was a mild solar lull, not a mini ice age. Number 45, when the Milky Way and Andromeda meet. Our galaxy and Andromeda are slowly drifting together. When they finally mix, their stars won't crash like cars, space is mostly empty, but gravity will stretch them into long tails and streams, and lots of gas will be stirred to make new stars. Over a very long time, the two spirals will settle into one big elliptical galaxy. New studies say the timing, and even whether they fully merge soon, is less certain, about a 50-50 chance within the next 10 billion years, but whenever it happens, the show will be huge and beautiful. Number 46, space tornadoes. High above us, Earth's magnetic bubble can twist into space tornadoes, swirls of charged gas that speed particles around like a cosmic blender. These storms can ruffle GPAs and radio for a bit and help make bright auroras. Scientists have even spotted a space hurricane over the North Pole. It spun for hours with a calm eye, but it was made of plasma, not rain. Missions like MMEs watch how these swirls form so we can predict space weather better. Number 47, spacequakes. Spacequakes are like magnetic earthquakes in Earth's space bubble. They happen when a speedy solar wind pushes and twists our magnetic field. This can make auroras dance and send little electric surges into the ground. Those surges can bother power grids and some radio or GPIAs for a bit. Number 48, a narrow river of dark matter hits Earth. Dark matter is invisible stuff that doesn't interact with light. We only notice it by its gravity. If a dense stream of it passed through us, you wouldn't feel it, no zaps, no burns, because it barely interacts with atoms. Scientists would look for tiny gravitational clues or delicate detector signals while knowing the average dark matter amount near the sun is small, about 0.3 giga-electron-volt per cubic centimeters. So any effect on orbits or satellites would be minuscule. Dark matter is a quiet neighbor that's hard to see and even harder to feel. Number 49, planetary rings and skies get hit too. Jupiter and Saturn don't just sit there. Space rocks smack them, leaving dark bruise spots we can see from Earth. Those hits stir their air with shock waves, great labs for learning about big impacts safely from far away. Saturn's rings also feel tiny hits from dust and micrometeoroids that chip away at the ice and make odd ring features. Some ring bits even rain down into Saturn's air and heat it up, a wild, real thing called ring rain. The sun can shock their magnetospheres, lighting up huge auroras, space northern lights on Jupiter and Saturn. Number 50, if a pressurized dome on Mars failed, Mars's air is only about 1% of Earth's, so inside domes we keep Earth-like pressure. If a dome ripped, air would rush out, making it freezing and airless in seconds. People would need suits or a backup shelter right away. That's why designs use strong layers, backups, and automatic seals, and why crews practice emergencies. Number 51, space radiation slowly adds up on Mars. Mars has no global magnetic shield, so cosmic rays reach the ground. Curiosity's RAD instrument measured about 0.67 millisievert of radiation per day on the surface, and even more during the trip in space. Over months, that adds up, which can hurt our cells. So habitats plan thick shielding like regolith or water walls, storm shelters, and smart work schedules to cut dose. Number 52, the Mars Climate Orbiter crash. Two teams used different units. One sent thruster data in pound seconds, the other expected Newton seconds. The tiny math mismatch nudged the spacecraft too close to Mars, so it was lost in 1999. Lesson: in space, even small unit mix-ups can doom a mission. Number 53, the surprise comets. Some comets dive in from the distant Oort cloud on long, lopsided paths and move very fast. We often discover them late, leaving little time to react. Experts say even 2 years' warning can be really short for a comet. Their glowing tails look pretty, but the icy rock cores can be big enough to do serious damage if they hit. That's why surveys and new missions aim to spot these speeders sooner. Number 54, a free-floating planet passes near us. Space has rogue planets that don't orbit any star, they just wander. If one drifted near our solar system, its gravity could nudge the faraway Oort cloud, the huge bubble of icy comets, and send a few comets inward. We know close flybys can do this. A small star nicknamed Schultz's star likely skimmed our Oort cloud 70000 years ago, and Gliese 710 is expected to pass through it in about 1.3 million years. Even so, models say our planets stay very stable. Big orbit shakeups are unlikely on human timescales. Number 55, a neutron star zooms past our comet cloud. A neutron star is a super small, super heavy star remnant with huge gravity and sometimes strong X-ray and gamma-ray beams. Far from the planets is the Oort cloud, a giant bubble of icy comets around our solar system. If a neutron star ever passed through that region, its gravity could jiggle lots of comets, sending some toward the inner solar system over many years. Like shaking a snow globe, and a few flakes drift in later. A neutron star also shines in high-energy light, so if it came very close, nearby space could get a dose of extra radiation, another reason we'd notice. Number 56, long-period comets, rare danger, big energy. Each year, about 10 long-period comets as big as 1 kilometer swing through paths that cross Earth's orbit, but space is huge, so the chance any one of them actually hits us is tiny. These visitors fly really fast, tens of kilometers per second, so if one ever did hit, it would release enormous energy, much more than a same-size asteroid, making it a serious but very unlikely threat. Number 57, grabbing a strange moon could shake things up. If Earth or a nearby planet captured a wandering moon, the extra gravity could change tides and gently tug on the planet's spin and other moons. We've seen captures before. Neptune's big moon Triton was likely captured, and that event probably wrecked or reshaped Neptune's earlier moon system. Many outer planet moons are irregular captures. Showing this is possible in nature, captures can also set up gravitational resonances that disturb orbits. Number 58, hidden crater collapses near lunar bases. Some places on the moon hide pits and lava tube caves under a blanket of dust. If a base sat over a weak spot and the ground collapsed, falling rock and dust could bury habitats, block doors, and fling debris farther than on Earth. No air plus low gravity. That's why teams use LRU maps and careful site selection rules to avoid sinkholes, steep crater rims, and landslide-prone slopes, and to test structures for shakes from moonquakes and impacts. Number 59, burps of gas from under the moon's surface. The moon has a super-thin exosphere, a wisp of gas made mostly of helium, neon, and argon. Some of that argon seeps out from the rocks made by natural radioactive decay, and its amount changes with time, which spacecraft have measured. That means the moon sometimes has little gas burps. Near a base, a sudden burp could briefly fog sensors or tweak air in tunnels, so future habitats will watch and vent carefully. Number 60, asteroid 2024 YAR-4 and the moon. Asteroid 2024 YAR-4 isn't a danger to Earth. That part's been ruled out. But there's a small chance, about 4%, it could hit the moon in 2032. If it did, the moon would take the punch. No air to slow it, and some tiny bits of lunar debris could fly into space, mostly a problem for satellites, not people. For scientists, the 2029 and 2032 observations are a big learning chance to test tracking and defenses. Number 61, lunar ejecta-meteor storms. If a rock smashes the moon, the hit can throw tiny moon bits into space. Some pieces get fast enough to escape the moon, and over years, a few can drift toward Earth, showing up as small meteor showers or extra dust that can bother satellites. We know this can happen because impacts constantly vaporize and eject material from the lunar surface, and scientists have even found lunar meteorites on Earth. Number 62, high-altitude space lightning caught from the International Space Station. In July 2025, astronaut Nicole Ayers snapped a rare flash above storms over Mexico and the IUS from the space station. These quick flashes are called transient luminous events. They pop above thunderclouds, not inside them. At first, people said sprite, but NASA later said Ayers actually caught an even rarer gigantic jet. Lightning shooting up toward space. Sprites look reddish and jellyfish-like. Gigantic jets can rise 50 to 90 kilometers high like a blue tree dot. They quote super fast and hard to see from the ground, so the AISS is a perfect lookout. Number 63, if an orbital station lost oxygen, astronauts need steady air. On stations like the International Space Station, special systems constantly watch and refresh the air and water. If a leak happens, alarms go off, crews isolate the leak, and ground teams use plans to fix it. This has worked during past small air leaks that weren't dangerous. Redundant gear and emergency procedures keep people safe while pressure is restored. Number 64, if a space elevator under construction collapsed. A space elevator is a hypothetical elevator that connects the surface of a planet to space with a giant wire of 35786 kilometers long and reaches the ground. If it snapped, falling parts could damage things below and make debris in orbit. That's why studies focus on ultra-tough materials, careful tether dynamics, debris avoidance, and strict safety rules before anyone builds one. In short, amazing idea, but safety engineering comes first. Number 65, solar superstorms can make metal clouds in our sky. Sometimes a really strong solar storm shakes Earth's upper air and makes thin, traveling metal clouds called sporadic E-layers. These clouds are packed with tiny ionized metal atoms like iron and magnesium from meteors that can mess with radio and GPIs for a while. In May 2024 storms, scientists saw these metal sheets surge worldwide and race around the globe, a big clue for how space weather touches everyday tech. Number 66. What if we faced an active galactic nucleus? An active galactic nucleus is a galaxy's monster black hole gobbling gas and blasting X-rays, gamma rays, and jets like a cosmic blowtorch. If our solar system sat close to one, that harsh radiation could strip atmospheres and be bad for life. Luckily, we're far from the Milky Way's center, tens of thousands of light years, and our own black hole isn't active like a quasar. So this is a cool idea to learn from. Not a problem today. IGENS, or active galactic nucleus, show how powerful galaxy centers can be when their black holes feed. Number 67. Cosmic rays are tiny chemistry hacks in the sky. Fast space particles called cosmic rays zip into our air and ionize gases like nitrogen and oxygen. That sparks chemical chains that make nitrogen oxides, which can eat some ozone high up. Most days it's small, but during big space events we can see the effect more clearly. Studying this helps scientists protect tech, flights, and people, and learn how space talks to our atmosphere. Number 68, we keep watch on space rocks, and the lists are public. Scientists track near-Earth objects known as NIU every day, and post close approach tables online so anyone can see which space rocks are zooming by. How close and how fast. NASA's CINEUS page lists upcoming and recent flybys with dates, distances, and speeds, and even computes approaches from 1900 to 2200. The Coordination Center shares a similar, frequently updated list and a risk list showing any object with a tiny non-zero impact chance. Number 69, Earth-grazing fireballs. They're super bright meteors that skim Earth's air at a very shallow angle, then zip back into space. While skimming, they can lose a little mass and even change their orbit before leaving. Sometimes tiny pieces break off and fall as meteorites, but most of the rock keeps going. A famous one was the 1972 Great Daylight Fireball, seen in daytime as it passed 57 kilometers above the IUS in Canada. Another zipped over Czechoslovakia and Poland in 1990 and then escaped back to space. NASA calls any very bright meteor a fireball. Earth grazers are just fireballs that don't fully dive in. Number 70, metal ring crash. A huge metal ring fell from the sky into a Kenyan village on December 30th, 2024, about 8 feet wide and 500 kilograms, as heavy as a car. Officials say it was likely a rocket separation ring. Thankfully, no one was hurt. People saw it land red hot in Mukuku village, and the Kenya Space Agency took it away to study. Most debris burns in the air, but big pieces can sometimes reach the ground. Number 71, life extinctions via cosmic ray events. A nearby supernova can flood space with cosmic rays for years, gently changing our air chemistry. That can nibble ozone, letting in extra IUV. One-way space blasts might stress life. We even find past supernova fingerprints on Earth, like iron 60 in ocean crust. Some scientists think such bursts help past die-offs, but it's still under study. The distance matters a lot. Closer has stronger effects. Far has tiny. Either way, Earth's atmosphere blocks most space radiation most of the time. Number 72, the Carrington-level solar storm. It's the biggest kind of space weather. A huge blast from the sun hits Earth's magnetic bubble and supercharges it. That's what happened in 1859's Carrington event. Auroras lit the whole planet and telegraph systems sparked and failed. Today, a storm could knock out power grids, jam GPIs and radio, and mess with satellites for days. Space weather centers track these storms and issue alerts using scales like KP, the Aurora Index. Big studies say the economic hit could be trillions if one struck modern tech. Number 73, the Kuiper Belt gets nudged. Far beyond Neptune is a big donut of icy mini-worlds called the Kuiper Belt. Sometimes Neptune's pull or a far-off passing star gives this donut a little nudge. So a few pieces get bumped inward and become comets we can see near the sun. Over long times, these worlds can also bump into each other, making smaller bits. So the Kuiper Belt isn't still, it's a slow, busy traffic circle that sometimes sends visitor comets our way. Number 74, the Apollo-Soyuz toxic fume scare. During the 1975 splashdown, the Apollo crew didn't shut off the capsule's small thrusters after the parachutes opened. Their fumes, nitrogen tetroxide, got sucked into the cabin through an air valve, making the astronauts sick, but they recovered after treatment. Today, procedures are stricter to avoid this. Number 75, Apophis, the famous flyby that's now safe. A big space rock called Apophis will zoom past Earth on April 13th, 2029. It will come closer than many TIV satellites, but it will miss us safely. Scientists checked carefully and said there was no impact risk for at least 100 years. That close pass is a science party. We'll study how Earth's gravity tugs the asteroid. Europe even plans a Ramses mission to watch Apophis during the flyby. Number 76, largest cosmic explosion. Imagine a black hole slurping a giant gas cloud for years, like a vacuum that won't quit. That's at 2021 AIYX, brighter than almost any known blast, and it kept glowing for years. Not months, it's about 8 billion light years away, so we see it as it was long ago. Astronomers think the black hole tore the cloud apart and turned it into light. Big telescopes watched it grow and change to figure out what's happening. Number 77, ultra-power cosmic ray Amaterasu. Sometimes a single space particle arrives with crazy energy. The Amaterasu particle hits Earth with about 240 exa-electron volt, one of the strongest ever seen. It was caught by the telescope array in Utah. Scientists first saw the event in 2021 and reported it in 2023. It seemed to come from an empty patch of sky, so its source is still a mystery. Don't worry, such particles don't hurt people on the ground. Our air takes the hit and makes a big air shower high up. Number 78, Lhasa Giant Gamma Ray Bubble in Cygnus. A huge telescope in China called Lhasa found a giant bubble in the Cygnus part of the sky that glows in super energetic light. This light is gamma rays so powerful they top 1 teraelectron volt, with the strongest seen at 2.5 teraelectron volt. That's way beyond anything we make on Earth. The bubble means there's a super accelerator inside, like a space particle booster. It likely speeds up protons to around 10 or 20 teraelectron volt. When those protons hit nearby gas, they make the gamma rays we see. Astronomers map the bubble and its hotspots to learn where the power comes from. Number 79, weird X-ray flashers in our neighbor galaxies. Astronomers found 29 strange X-ray objects in the Magellanic Clouds, 2 small galaxies next to ours. Sometimes they suddenly get 20 times brighter and stay that way for months. Then calm down again. It's like quiet campfires that turn into brief bonfires. Scientists think these may be a new class of objects nicknamed millinovae, where a dead star gets fresh fuel and flares. Finding them tells us surprising X-ray bursts are more common and varied than we thought. If a similar one were much closer, its high-energy light could matter for satellites and space weather, but these are far away. So they're great laboratories to learn how stars flare without being scary for Earth. Number 80, Yarkovsky effect, the sunlight's tiny push on asteroids. Sunlight warms one side of a spinning asteroid. Later, that warm side glows heat back into space like a tiny thruster. That gentle push can speed up or slow down the rock, changing its orbit very slowly. If it spins one way, the orbit can grow. The other way, it can shrink. The push is tiny each day, but over years to centuries, it adds up. That's why scientists track this effect to predict paths and check if any rocks might come close to Earth. A warm pebble with a heat engine so small you can't see it. But space feels it. Number 81, interstellar comet and solar blast. A visitor from far away, Comet 3 AI Atlas, flew through our solar system and even took a hit from a big solar outburst, a CIMI, without falling apart. Scientists are watching to see if that hot, fast blast changed its surface or path. The comet isn't dangerous to us, it stays far from Earth, but it's perfect for learning how space rocks handle the sun's weather. Think of it as a tough snowball testing a giant hairdryer. Number 82, Chelyabinsk lesson. In 2013, a space rock about 20 meters wide exploded high over Chelyabinsk, Russia. The shockwave shattered windows and injured around 1,500 people. Mostly from broken glass. No one saw it coming because it approached from near the sun's glare. This event taught the world that even small asteroids can cause local trouble, and it boosted efforts to find and track more of them. Number 83, a day-long cosmic blast. Most gamma-ray bursts are quick, seconds or minutes, but in 2025, telescopes saw one called GRB 250702 that lasted about a day, way longer than usual. Scientists are still studying what could make such a long, powerful glow, maybe a rare kind of black hole feeding event. It didn't happen anywhere near us, but it teaches us how wild the universe can be. Number 84, Tunguska-style mysteries. In 1908, something exploded over Siberia and flattened forests for miles. No big crater was found, so scientists think it was a space rock that blew up in the air. An airburst. The blast was like millions of tons of TNT, but the area was remote, so few people were hurt. Tunguska shows how space can surprise us even without a crater and why we hunt and track near-Earth objects today. Number 85, South Atlantic anomaly, the bumpy spot in Earth's magnetic shield. High above us are two donut-shaped radiation belts of fast particles held by Earth's magnetic field. In one place, over the South Atlantic, the inner belt dips closer to Earth. That dip is the South Atlantic anomaly, or SAIAI. Satellites flying through the SAIAI get extra particle hits, so engineers may switch instruments off or add shielding to avoid glitches. For people on the ground, it's not dangerous. The effect mainly bothers space tech. Think of it like a pothole in our planet's magnetic road. Spacecraft slow down and drive carefully. Number 86, extra Van Allen radiation belts. High above Earth are two donuts of trapped radiation called the Van Allen belts. During big solar storms, those belts can shift, puff up, or even sprout extra belts for a while. Scientists saw a temporary third belt in 2013. And new data show extra belts appeared after the big May 2024 storm. These changes happened because solar blasts shake our magnetic bubble and move high-energy particles around. That's exciting science, but tough on satellites and astronauts since extra radiation can zap electronics. So space weather teams watch the belts closely to keep space tech safe. Number 87, SGR 180620 magnetar superflare. On December 27, 2004, a tiny but super strong star called a magnetar blasted a giant flare of X-rays and gamma rays. It was so bright that for a moment it was the strongest flash from beyond our solar system ever seen. Even from about 5,000 light-years away, it tickled Earth's upper air, making extra electricity or ionization. Instruments saw our ionosphere jump like the planet briefly rang from the distant blast. This showed how powerful magnetars are, with magnetic fields trillions of times stronger than a fridge magnet. Number 88, Interstellar Visitor 2, AI Borisov. In 2019, an amateur astronomer named Gennady Borisov spotted a comet that wasn't from our solar system. It came from another star. Scientists confirmed it was the first known interstellar comet named 2 AI Borisov. It whooshed around the sun in December 2019 and never came close enough to be dangerous. Just a quick visit, telescopes found it had lots of carbon monoxide, meaning it likely formed in a very cold place far from its own star. Even its light-scattering sparkle looked different from most comets we know. Another clue it was truly alien. Number 89, Eta Carinae's Great Eruption Light Echo. A giant star called Eta Carinae had a huge tantrum in the 1800s, blowing off lots of gas. That old flash of light bounced off space dust and is only reaching us now. A light echo. By studying the echo, scientists can replay the blast and measure how fast the gas flew. They even learned the eruption was cooler than expected and may have thrown out more than 10 tons of material. It's like hearing a clap seconds later in a canyon, an echo that lets us study the past. Number 90. Comet Holmes's sudden glow-up. In 2007, quiet comet 17 Pi Holmes suddenly got millions of times brighter in about 2 days. It jumped from so faint only big telescopes saw it to a naked eye bright. Round, fuzzy star. This surprise outburst likely came from fresh dust and gas blasting off its surface. People all over Earth looked up and saw it in the Perseus constellation. It's a perfect example of how comets can be sleepy one night, spectacular the next. Number 91, Lachamp's excursion when Earth's magnetic field got wobbly. About 42000 years ago, Earth's magnetic field got very weak and the poles wandered. That let more space radiation reach our air, which scientists can see today in tree rings and other records. During this time, the aurora likely shifted and the upper atmosphere changed. It wasn't a doomsday, but it was a big space weather test for our planet. Researchers now use rocks, ice, and ancient trees to time the event and study its effects. Number 92, AID 775 Cosmic Spike, a big blip in tree rings. Around the year 775, trees around the world suddenly showed extra radiocarbon in their rings. That means Earth got hit with a burst of high-energy particles, likely a huge solar storm. We didn't have satellites then, but the trees kept the receipt. Scientists also see matching signals in ice cores. So we know it was global. These rare spikes help us learn how big space storms can get and how they might affect tech today. Number 93, changes in cosmic rays when our shields weaken. Earth has two shields. The sun's big bubble, the heliosphere, and our own magnetic field. They help block some space radiation called cosmic rays. If either shield gets weaker, more cosmic rays can sneak in, making the upper air extra sparkly and sometimes bothering electronics and satellites. Big solar eruptions can also change cosmic rays for a while, sometimes reducing them, sometimes letting different particles through and shaking up our space weather. Scientists track these ups and downs with the sun's 11-year cycle to keep planes, power, and satellites safer. Number 94, long ago rock storm, the late heavy bombardment. Billions of years ago, the inner solar system went through a long smashing time when tons of asteroids and comets hit the moon. Earth and neighbors, craters on the moon are clues. This era is called the late heavy bombardment. Scientists still study how big it was and when it peaked, but it definitely shaped young planets. Some models link it to the giant planets moving around, stirring up space rocks and sending many inward, showing what it's like when lots of big impacts happen. Number 95, off-axis gamma-ray burst cocoon. Even if Earth isn't in a gamma-ray burst's main beam, some gamma and X-rays leak sideways from its hot cocoon and the long-lasting afterglow. That light can zap the upper air, making it extra electric. Models show strong bursts can thin the ozone layer, letting more IUV reach the ground. So even off-axis radiation could matter if the burst is nearby. But GRBs close enough to hurt us are very rare. Number 96, an alien probe might already be here. Some scientists like Harvard's Avi Loeb once wondered if odd space visitors such as Oumuamua could be artificial, like a tiny robot scout. Most astronomers think natural explanations fit better, ideas like a nitrogen ice shard or other fragile space ice that pushes itself a bit as it warms. So the simple take, it's fun to ask, but the boring answer is most likely. When new interstellar visitors show up, NASA and other teams check carefully and look for plain vanilla physics first. Number 97, could a lab make a mini black hole? If scientists ever made a tiny black hole, it would be so small it would evaporate instantly by a process called Hawking radiation. Poof, gone, so it couldn't eat anything or hurt us. Big safety reviews for particle colliders say these ideas are safe. And nature already makes higher energy collisions all the time with cosmic rays hitting Earth, the moon, and the sun. No disasters. In short, a lab-made mini black hole would be a blink and vanish speck. Not a danger. Number 98, if a quasar near us went boomier, a quasar is a galaxy's monster black hole gobbling gas and blasting out light and jets that can push on gas across the whole galaxy. If one were truly nearby and suddenly got much brighter, its radiation could be rough on nearby planets and make sky-bright fireworks we could see. Luckily, the quasars we study are very far away. A famous one, 3Ci 273, is 2.5 billion light-years, so they're spectacular but not a danger to Earth. Number 99, daylight radio blackout from big solar flares. Sometimes the sun pops a huge flare, an X-class, and its X-rays make the sunlit air over Earth extra electric. That can knock out HEF radio and mess with GI-PIEs on the daytime side. Pilots, ships, and emergency teams feel it first. Space weather centers use an AR scale, R1 to R5, to rate how bad the blackout is, and they send out alerts so people can plan. Number 100, ocean impact mega tsunami. If a space rock splashes into the ocean, it can shove up the sea and send huge waves racing across a whole basin, wrecking coasts far from the splash. Scientists model these tsunamis to see how big and how far the waves go. And to improve warning tools, the dino killer Chicxulub strike made a global mega tsunami far beyond anything in human history, and that's all. What space disaster fact surprised you the most? Leave it in the comments and subscribe. See you soon, your friend Neil.